In this video, I will be discussing reduction formulas in integration. In the previous videos, if you have seen my videos on integration by parts, there are actually integrands that we apply integration by parts more than once. And you have seen that the labor of work is very long because it involves a successive applications of integration by parts to evaluate an integral. So applying integration by parts repeatedly for a particular integrand is a very cumbersome process. Now, to illustrate, we will have this illustration here. Suppose we need to solve the integral of x to the power 10 times e to the negative x dx. This integrand can be solved using integration by parts because this is a product of two functions, the algebraic function which is x to the power 10 and the exponential function which is e to the power negative x. Actually, if you do it the usual way, we will be applying integration by parts here 10 times for this integrand. And each time we apply the integration by parts, this x to the power 10 will be reduced to an exponent which is 1 less from the given exponent. Since this is very repetitive and tedious, we prefer to use a reduction formula for this one. So to solve this one, we need to derive a reduction formula first. So solving for the reduction formula, we have to generalize this integral as x to the power m times e to the negative x dx here. So we generalize this 10 as m exponent and we call this integral as integral im. So this is our representation. So applying integration by parts, we let the first part as our u here. So u is x to the power m and our dv here is the e to the negative x dx, and solving for our du, we have m times x to the power m minus 1 dx. But for our v, we need to integrate our dv, so we have the integral of e to the negative x dx here, and to integrate the e to the negative x, we should have a negative dx here as the differential of negative x. So to neutralize the added negative here, I need to have a negative in front of the integral. So therefore, our v is equal to negative e to the power negative x. So by substitution here, we have this x to the power m as our u and this e to the negative x dx as our dv here. So this is our u, which is x to the power m, and according to the formula, our im is equal to uv minus the integral of v du, because the integral of u dv is uv minus the integral of v du. So substituting our representations above, our u, which is x to the power m, will be multiplied to our v, which is this one, negative e to the negative x. And this will be subtracted by the integral of v, which is the negative of e to the power negative x. And then this will be multiplied by our du, which is this one here, the m times x to the power m minus 1 dx. So simplifying our answer, for our m integral. This is negative x to the power m times e to the power negative x plus, because the negative of the negative is positive, plus m, because m here is a constant. So m times the integral e to the negative x times x to the power m minus 1 times dx. And rewriting our answer, we have negative x to the power m times e to the power negative x plus m times the integral of x to the power m minus 1 times e to the negative x dx. And you can observe that this integrand is almost the same from our given integrand, but the exponent of x is 1 less than the exponent of this x here, because our exponent here is m minus 1. So this one is already a reduction formula, because we have successfully reduced the exponent of x to the power m to x to the power m minus 1. So I can write here my im, which is equal to negative x to the power m times e to the power negative x plus the m times the I sub m minus 1, because this is just the same with our im, but the exponent is 1 less. So applying this one to our given integrand, which is this I sub 10, because the exponent of x is 10, we have I sub 10, which is equal to the integral of x to the power 10 times e to the negative x dx. And this I sub 10, when applying this formula here, so our m is 10, so this becomes negative x to the power 10 times e to the negative x plus 10 times I sub 9, because our m is 10, so 10 minus 1, that's 9. So applying again this formula here, but this time our m is 9. So finally we have I sub 10, which is equal to the negative x to the power 10 times e to the negative x plus 10 times negative x to the power 9 times e to the negative x plus 9 times I sub 8 there. So multiplying this 10 to each term inside this square bracket here, we have I sub 10, which is equal to negative x to the power 10 times e to the negative x minus 10 times x to the power 9 times e to the negative x plus 10 times 9, because the 10 will be multiplied to 9 times I sub 8. And applying again I sub 8, we have I sub 10, which is equal to negative x to the power 10 e to the negative x minus 10 x to the power 9 e to the negative x plus 10 times 9 times your I sub 8. So your m this time is 8. So this is negative x to the power 8 times e to the negative x, following this formula, plus 8 times I sub 7 here. And multiplying our constant of 10 times 9, we have negative x to the power 10 times e to the negative x minus 10x to the power 9 times e to the negative x minus 10 times 9 times x to the power 8 e to the negative x, because positive times negative is negative. And then we have plus 10 times 9 times 8 times I sub 7. And then again, we need to apply our reduction formula here. So we have negative x to the power 10 e to the negative x minus 10 x to the power 9 times e to the negative x minus 10 times 9 x to the power 8 e to the negative x plus 10 times 9 times 8 times our I sub 7, which is negative x to the power 7 times e to the negative x plus 7 times I sub 6 here. So simplifying our answer here, we need to factor out the common factor in these terms here, which is the negative of e to the negative x. So we have x to the power 10 for this term, and then plus 10x to the power 9 for this term, because we need to factor this e to the negative x and the negative, and then plus 10 times 9 times x to the power 8, because this negative e to the negative x will be factored outside. So we have this one plus 10 times 9 times 8 times x to the power 7, because this negative of e to the negative x will be factored also here. And then we close this one. So this will be added by 10 times 9 times 8 times 7 times I sub 6, because this one will be multiplied to 7I sub 6. And then repeating this process until this will reach to 0, we have negative e to the negative x times x to the power 10 plus 10x to the power 9 plus 10 times 9 x to the power 8 plus 10 times 9 times 8 times x to the power 7 plus and so on and so forth until you will reach 10 times 9 times 8 times until the last number 2. And then we have here x to the power 1, because you can check the pattern. If this is 9, the exponent of x is 1 less. So you see here 8 times x to the power 7, the exponent of x is 1 less to the coefficient here, which is 8. So if this is 2, the exponent of x is 1. And this will be added to 10 times 9 times 8 times 7, but this is 1 less from the coefficient here. So if this is 2, 1 less is up to 1. So 10 times 9 times 8 times 7 up to 1, which I can represent it as 10 factorial. And this is multiplied by I sub 0. And applying for the last time the I sub 0 there. So we have negative e to the negative x times x to the power 10. And this can be represented as 10 factorial over 9 factorial. Because 10 factorial is a product from 10 to 1. But 9 factorial is a product from 9 to 1. So 10 to 1 divided by 9 to 1, what will remain is 10. And this is multiplied to x to the power 9. And also this 10 times 9 can be represented by 10 factorial divided by 8 factorial. And this is multiplied by x to the power 8 plus 10 factorial divided by 7 factorial. Because 10 factorial divided by 7 factorial is this one here, 10 times 9 times 8. And this is multiplied by x to the power 7 plus and so on and so forth until you will reach 10 factorial divided by 1 factorial, which will be multiplied by x to the power 1, because the pattern is when the exponent of x is 9, the denominator is 9 factorial. And when the exponent is 8 for x, the denominator is 8 factorial. So if this is 1 factorial, the exponent of x is 1. So this is it. And this will be added to our 10 factorial times I sub 0, which is negative x to the power 0, which is 1. So negative 1. So negative 1 times e to the negative x is negative e to the negative x. And we stop because this is already 0. And the result will be added to the constant of integration, c. So combining this one by factoring also our negative e to the negative x here as 1, we have negative e to the negative x times x to the power 10 plus 10 factorial over 9 factorial times x to the power 9 plus 10 factorial over 8 factorial times x to the power 8 plus 10 factorial over 7 factorial times x to the power 7 plus, and so on and so forth until you have 10 factorial divided by 1 factorial times x to the power 1 plus this one 10 factorial can be represented as 10 factorial over 0 factorial times x to the power 0, because I don't have x here, and then I need to factor out this one here plus the constant of integration c. And this is my answer when I want to integrate my x to the power 10 e to the negative x dx here. So this is how to apply this integration formula, which is a reduction formula. So actually in this example we are applying integration by parts 10 times here, but the length of work was reduced by using this reduction formula that we derive here. So reduction formula is very important when you want to perform an integration that needs to apply integration by parts more than once, because it will reduce the amount of work required. So here in this example, what is the reduction formula for this one? So to solve for a reduction formula, we have to apply integration by parts for this one here. And in this case, to apply, we need to break down this m power of sine x as sine to the power m minus 1 x times sine x dx here. And you can check that sine x times the sine x to the power m minus 1 is just sine x to the power m, because the exponent of sine x here is 1 and the exponent of sine x here is m minus 1. So adding the exponent m minus 1 plus 1 is just m. And why is it that we do that one? We do that one in order for us to apply integration by parts. Because if this is our u here, so representing our u as sine x to the power m minus 1, and for our dv as sine x dx here, we can solve for our du using the power rule, which is m minus 1 times the sine x to the power m minus 2. And by the chain rule, we need to find the derivative of the base, which is sine x, as cosine x dx here. And then for our v, we need to integrate our sine x dx. And we know that the integral of sine x dx is negative cosine x. So if this is our u, this is also our du. And if this is our dv, this is also our v here. So substituting this one to the given integrand, we have the integral of u, because instead of writing this one, we will write its representation as u. And this is multiplied by dv because this one is represented as our dv. And the integral of u dv by the formula of integration by parts is uv minus the integral of v du here. So substituting our representations, we have our u, which is sine x to the power m minus 1 times v, which is negative cosine x, minus the integral of our v, which is negative cosine x, times our du, which is this one here, which is m minus 1 times sine to the power m minus 2 of x times cosine x dx. So simplifying our answer, we have negative cosine x times sine to the power m minus 1 x plus m minus 1, because m minus 1 here is a constant and the negative of the negative is positive here. So this is multiplied by the integral of sine to the power of m minus 2x times cosine squared x dx, because we have two cosines here. So cosine x times cosine x is cosine squared x. But this integrand needs to be simplified in order to integrate, and to do that is to apply trigonometric identities. So we have negative cosine x times the sine of m minus 1 of x plus m minus 1 of the integral of sine x to the power m minus 2 times 1 minus sine squared x, because we know that cosine squared x is equal to 1 minus sine squared x by Pythagorean identity. So distributing this one to this binomial here, we have negative cosine x times sine x to the power m minus 1 plus m minus 1 times the integral of sine x to the power m minus 2 minus sine x to the power m quantity dx. Because when you distribute this 1 to 1, this is our answer. And this also, when multiplied to this one here, the exponent will be added. So m minus 2 plus 2 is just m. So applying the integral of a difference, we have negative cosine x times sine x to the power m minus 1 plus m minus 1 times the integral of sine x to the power m minus 2 dx minus the m minus 1 of the integral of sine x to the power m dx, because this m minus 1 should be distributed to the two terms. And this is our answer when we integrate this sine x to the power m dx. And you notice that this one is also found here. So therefore, we need to eliminate this one here by adding both sides of the equation by the same integral. So adding at the right by this one, and also here by m minus 1 times the integral of sine x to the power m dx. So we are adding at the left, also adding at the right by the same quantity. So adding this 1 to 1, because this is understood to have a 1, we have m times the integral of sine x to the power m dx, which is equal to negative cosine x times sine x to the power m minus 1 plus m minus 1 times the integral of sine x to the power m minus 2 there. Since this one and this one cancels each other, but we need to eliminate this m here by multiplying both sides of the equation by 1 over m. So we have the integral of sine x to the power m dx, which is equal to negative 1 over m when multiplied by 1 over m here. So this is multiplied by cosine x times the sine x to the power m minus 1 plus m minus 1 over m times the integral of the sine x to the power m minus 2 dx. And you see that this is a reduction formula, because in our answer, although we have an integral still here, but the exponent is 2 less than the exponent of the given integrand. So it improves because this is a reduced exponent from the given integrand. Hence, this is our reduction formula for the integral of the nth power of sine x dx. And this is very useful when you are evaluating the integral of higher powers of sine x there. Say, what is the integral of sine x to the power 15? So you will apply this formula in evaluating the integral. So next example, number 2. We have find the reduction formula for the integral of x squared dx over the quantity a squared plus x squared to the power m here. So to solve for the integral of this x squared dx over the nth power of a squared plus x squared, we realize that the numerator is not the differential of the denominator, because the differential of this a squared plus x squared will only involve x dx. So what will I do is to factor out 1x from this x squared. So we have x times x dx over this nth power of a squared plus x squared here. And if we take this one as our u and this one as our dv here, then u is x and dv is equal to x dx over the nth power of a squared plus x squared. And solving for our du here, we have dx. And for our v from dv is we need to integrate this x dx over the nth power of a squared plus x squared here. And moving this denominator to the numerator, we have the integral of a squared plus x squared to the power negative m times x dx. And we know by the chain rule that the differential of this is not x dx, but it should be 2x dx, because the derivative of a squared is 0 since this is a constant, and the derivative of x squared is 2x, but we don't have a 2 here. That's why we need to neutralize by writing 1/2 in front of our integral symbol. So this is a squared plus x squared to the power negative m times 2x dx, because 1/2 times 2 is just a 1. So solving for the integral of this using the power rule is just 1/2 times the fraction of a squared plus x squared to the power negative m plus 1 over negative m plus 1 here. And rewriting this one, we have 1 over 2 minus 2m, because when I distribute these 2 to this constant negative m plus 1, we have minus 2m, which I have here, and 2 times 1, which is 2. But I need another factor, which is a squared plus x squared to the power m minus 1, because using the laws of exponent, when you move this one down, the exponent will be changed to its opposite sign. So this is now our v. Hence, by substitution, instead of writing x, I will write its representation, which is u. And instead of writing this one, I will write its representation, which is dv. And by the integration by parts formula, this is uv minus the integral of v du. So substituting back our representation, we have our u, which is x, and our v, which is this one here, 1 over 2 minus 2n times a squared plus x squared to the power m minus 1. And this will be subtracted by the integral of v, which is 1 over 2 minus 2m times a squared plus x squared to the power m minus 1 times du, which is dx. So simplifying our answer, we have x over 2 minus 2m times a squared plus x squared to the power m minus 1. And this will be subtracted by 1 over 2 minus 2m, because this 2 minus 2m is a constant here. And this will be multiplied by the integral of dx over a squared plus x squared to the power m minus 1. And this is our reduction formula for the integral of x squared dx over a squared plus x squared to the power m. And you observe that this is really a reduction formula because our answer involves an integral, but this integral is having an exponent which is 1 less than the exponent here. And you observe that there is no more x squared in the numerator. So this is now our reduction formula here for the given integral. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.